You are trying j of x on 205 using the vertical asymptote. What will make that denominator 0? So this is exactly what you had to do on last night's homework. And then we will talk about the rules to practice that 3-part rules. Does everyone have this packet? So you should have factored out an x squared, right? So x squared times x minus 2. So what values will make the denominator 0 when x is 0 or 2? So I have 2 vertical asymptotes that will make the denominator be 0. So then there's a 3-part rule. I'll put it up on the board in a minute, but you've got it back here on the previous page. You're going to compete between the numerator and denominator. So if the denominator wins, it's always y equals 0. If they're equal in power, like they're both quadratic functions or both linear, you strip the coefficients of x. And if you can do division, because the numerator has a bigger power, then you get a slant asymptote. So what's going on when I put the numerator against the denominator? I have a constant function and I have a cubic function. So the denominator wins. So my asymptote is just y equals 0, because when I plug in a big value for x, the denominator blows up. So 1 divided by like a billion would be 0. 0.000000001. All right, let's do the next page together because I think you need some practice. Why don't you go through first and try all of your vertical asymptotes on your own? So take a look at the denominator for each of these. If you want to try the horizontal asymptotes yourself, I'll give you a couple minutes, but then I'll go through the rules for the horizontal ones. I think you can do the vertical though. Any restrictions? Because it's x squared plus 4, I can never make this x squared a negative 4. So therefore, I will never get 0 in the denominator. So there are none. There's no vertical asymptote on this graph. There just isn't. All right. What was the vertical asymptote for n of x? It would be at x equals 0, right? Because 2 times 0 squared. And then on q of x, you didn't have to do any special work. It would just be at -1, because that would make the denominator 0. And then on the last one, it would just be x equals 0, right? So you're training your brain to see what are the bad values, excluded values for x. So let's go through now and use our 3-part rule, and then we're going to make our note card to do some of the graphs on the next page. So, all right, I look and see which is going to win in a competition. They're both quadratic functions, right? X squared over x squared. So I'm going to peel off the coefficients, and the coefficients of just the x squared terms are 2 over 1. So because the numerator equaled the denominator, the answer is 2 over 1. So y equals 2 is how you write your final answer. It's a horizontal asymptote at y equals 2. So that's going to be a horizontal dotted line right through 2. All right, what happens in n of x? Who wins? We've got a linear function over a quadratic function. Technically, I could have reduced this by 1 power of x, but then I would have still had 3 in the numerator, 2x in the denominator. So the denominator is still going to win. So when the denominator blows up, we know that it's just at y equals 0. Denominator gets bigger really fast. All right, q of x. This is one when you can do division. So because you've got a quadratic divided by a linear function, so if you could try doing your division over here, it's like an apple a day, it's like a division problem a day. Keep your division skills sharp. So try taking x plus 1 using the box method to do division. And I'll do it and then put it up. Did you also get a remainder of 10? The remainder of 10 doesn't really matter. So you put your 3x squared here, 3x goes on top, 3x times 1 is 3x, and then you need -5x in order to get to the -2x that you wanted in the dividend. So make sure that you don't put the -2x right there. The sum of your diagonal needs to be -2x. So then the answer is y equals 3x minus 5. It's going to be a slanted diagonal asymptote. And then on the last one, the denominator wins again, right? So y equals 0 is the horizontal asymptote. So that's your three-part rule for step number 4. So let's take a minute and write out your note card. And you can write it in whatever helps you write it best. But for a rational function, it's just I'm just going to write the 4 steps down. So your first step is to find your y-intercept. So how do you find a y-intercept? You're going to plug in 0 for all the x's, right? Plug in 0 for x. So if you want to put more detail, put more detail. But I guess as you're going through the problems today, you can figure out if your note card will suffice or if you need more detail on your own note card. All right, so step 2, I find my x-intercepts by setting the numerator, I'll write out numerator, equal to 0 and solving for x. So you set your numerator equal to 0 and solve for x, and that will give you your x-intercepts. And then step 3 is our vertical asymptote. Can I abbreviate asymptote? You set your denominator equal to 0 and solve for x. And then it's our 3-part rule. So I don't know if you'll have all the space you need on the front or not. I wrote kind of big, but so step 4 is your horizontal or slant asymptote. So it's the 3-part rule. So if the denominator is a bigger power, it's y equals 0 every time. If the numerator is equal to the denominator, you strip the coefficients of x. I can't fit the word coefficients, or you could write peel off the coefficients of x. And then if the numerator is a bigger power, you do division. So to me, that's enough for me to know what to do. But if that shorthand or stuff doesn't make sense to you, I can always give you another note card and you can write it out in more detail, however you want. This doesn't have to be your final note card. So if you feel like there's something else that you need for these 4 steps to make sense at the end of the day, just rewrite the note card however you want it to be. All right? So that's your note card. So we're going to kind of have this on the side of our desk, and we're going to keep referring to it as we go through kind of some of these practice problems. So these are the types of questions. Can I move the note card? You're still writing it, right? So I'm just going to, I get 6 divided by 3, right, which is 2. So my y-intercept is going to be at 0, 2. And I can go ahead and graph that right on the y-axis. I kind of graph it as I go. So your first step, right, on our note card says plug in 0 for x. So that's what I did. And I got 6 divided by 3 is 2. My next step is to find my x-intercept. So how do I find my x-intercept? I set my numerator equal to 0. Well, this numerator is fixed, right? It's a constant function. It's always 6. So there actually will be none, right? There's no x-intercept, probably because of an asymptote. We're going to find that out. I skip domain and range until the end of the problem. That way I can look at what the graph is doing and do it graphically. So my asymptotes, I always do my vertical asymptote first. So I go in order, step 1, 2, 3, and then 4 is horizontal. So my vertical asymptote, I'm going to set the denominator equal to 0. So I go back up to my function. If x plus 3 becomes 0, what does x have to be? -3. So my first asymptote is at x equals -3. So that's going to be a vertical line at -3. So go ahead and dot that on your axis. When you're doing these for practice, you may want to use a pencil, but we're doing this one together, so hopefully we won't make mistakes. All right, then our last step is we compare the numerator and the denominator to see if we have a horizontal or slant asymptote. This is a constant function and this is a linear function. So the denominator wins. So on my note card, it says when the denominator is bigger, the asymptote is always y equals 0. So my horizontal asymptote is at y equals 0. And that is kind of hard to draw on your graph, but I'll try to do it with a different color here. So it's basically the x-axis is my asymptote. And that should kind of fit with the fact that we said there was no x-intercept. All right, so then we use our two rules that asymptotes will always, or sorry, graphs will always hug their asymptote. So I just know that there's an elbow in this quadrant that goes right through my y-intercept and it hugs both of those asymptotes. So then I know, because this is a function, that there will be nothing down here beneath it, but I need to figure out, is the other elbow going to be like a volcano, or is it going to be kind of reflected over the origin? So to figure out where the other elbow goes, that's when you're going to plug in one additional coordinate for x in the original function. So if this asymptote is at -3, a good value to plug in for x would be -4. So in your original function, you're going to plug in -4 and see what you get as your output. 6 divided by -1 is going to be -6. So I know that at -4, the graph touches the point -6. So I can graph -4, 1, 2, 3, 4, 5, 6. And if that point is down there, kind of in that quadrant, I know that there's an elbow curve down here that goes through that point. So you only need one additional point in that kind of quadrant to figure out where the graph is, because it's always going to hug the asymptotes. All right, so there's my graph. Now I can analyze the domain and range. So as I skim from left to right, there's only one little hiccup on the graph, and that's at -3. So our domain is x cannot be -3. And then as I skim the graph up and down, there's only one spot that I cannot be for a y value. So y cannot be 0. So it will usually just end up being your two asymptotes. But I can think of one example when, like at the end, if your graph ends up looking like this, it's a volcano graph, instead of it just being y is not 0, the range could be y is strictly greater than 0, right? Because I have no elbow down here. So I always wait till the end to check what the domain and range are. I don't just assume that they are going to be exactly the asymptote every time. All right, so then this was just practicing that limit kind of analysis of the end behavior. So this says, as x approaches infinity, so that's the right side of the graph. What is the function approaching? So I'm actually talking about this arrow right here. What y value will that guy approach? It's going to approach 0 because this asymptote is 0. So as I go and keep going and keep going and keep going, I'm going to get closer and closer to just 0. And this is going to take some practice. So this part will not be on your quiz on Friday, but it will be at the end of this unit. You'll be asked that on your test. The next question says, as x goes to -infinity, so they're asking as x goes to the left, what is this arrow approaching? So this arrow is also approaching 0, your horizontal asymptote. And then they're asking you at that vertical asymptote. See, as x approaches -3. So what's happening at the asymptote is what they're asking. And there's a little tiny superscript of plus and a little tiny superscript of minus. The plus sign means on the right side of the asymptote, and the minus sign means on the left side of the asymptote. So like, here's my asymptote. This is to the right. and this is on the left. So on the right side of the asymptote, it's going up, and on the left side of the asymptote, it's going down. So on the right, it's going towards positive infinity, and on the left, it's going towards negative infinity. They're just asking you, where do all those arrows point to, basically? It's just the notation that's kind of tricky. So I'm actually going to skip example 2 because it's a very similar example to example 1. So you can come back to example 2 on your own, but I'd like to skip ahead and try example 3, because example 3 has a couple asymptotes. So I will not be giving you one like this on your quiz, but I want to show you how to analyze it, and then we'll look at the graph for our calculator for the graph. All right, so let's go through the 4 steps. The first step is your y-intercept. What do you get when you plug in 0 for x? You get 1 on top and -6 on the bottom. So 0, -1/6 is your y-intercept. So you just kind of graph it really close to 0, but you know that it's down below 0 on the y-axis. What's your x-intercept for this function? What will make the numerator 0? Nothing. So there's no x-intercept. And then we're going to skip our domain and range till the end. Our vertical asymptote, I need to actually factor this denominator to figure out what the bad x values would be. So I'm looking for the factors of -6, if I do the diamond, that add up to -1. So what are my 2 factors going to be? -3 and 2. So x minus 3, x plus 2, those are my factors. And so my asymptotes are the opposite of those factors. So I have one asymptote at +3 and one asymptote at -2. So this makes it a little bit more complicated because it gives you 3 regions of your graph. So I'm not going to have you do that on your quiz without looking at a calculator. I'm just going to give you kind of a double elbow. All right, so then what is my last asymptote? So look at your rule number 4. Who is bigger, the numerator, denominator? Denominator again, right? So y equals 0, and that's why there was no x-intercept. So on this one, you could plug in like an x value over here, and you could plug in an x value over here. But in the middle, sometimes there's some weird things where it actually will cut through the asymptote. So I'm not going to give you anything to try to, trick you. I'm just going to, let's look and see if we were going to analyze it from a calculator, what it would look like. So in this case, it's basically 2 elbows, and then this kind of looks like a parabola through the y-intercept, but sometimes it might cut through. I know it seems weird, but it could cut through the asymptote in one region and stay asymptotic in the other 2 regions. So in this case, I'm just going to sketch what it looks like. I know I didn't find my coordinates, but it just kind of was like the parabola graph with the 2 elbows. So in the case of multiple vertical asymptotes, I would put that on a calculator section so you could analyze any tricky parts with the calculator. All right, so my domain is just the 2 excluded x values. X cannot be 3 or -2. And then my range is basically still just my asymptote. Y cannot be 0. All right, so I'm going to skip example 4, and I'm going to jump down to 5 and 6, and then leave you with the couple that I didn't do. Maybe you'll get to 7 and 8 too, I don't know. But all right, example 5, this is a different looking rational function because I noticed my powers have kind of shifted. So let's go in order. What's your y-intercept first? So if you plug in 0 for the x's, what is your output? -9 divided by -1. So 0, 9 is my y-intercept. So there I am. And for my x-intercepts, I'm looking at my numerator here. It's a quadratic that's factorable by difference of squares. So I could factor it into x plus 3, x minus 3. So I actually have two x-intercepts this time. So my two x-intercepts are at 3, 0 and negative 3, 0. So I can plot my two x-intercepts on my graph. Skip domain and range for now. What's my vertical asymptote? So now I just tunnel vision and look at my denominator. So what would be the bad x value when x is 1, right? So my asymptote is x equals 1. So that will be a vertical line at x equals positive 1. And your last step is going to be, you might need to find a little scrap of paper or something, but you're going to have to do division. X squared minus 9, you may want to write it as x squared minus 0x minus 9, just so that you don't end up missing that there are 0 x's. So take a minute, maybe you can find a little scrap. There's a little bit of space on the next page, but I'll just kind of do mine down here at the bottom, I guess. So I'm going to pause it. I'm going to let you. So you put x squared, x times x is x squared. So x times negative 1 is negative 1x, and you need to get to 0 x's. So positive 1x will give you 0. So y equals x plus 1. So what does that look like? I had a remainder of negative 8. The remainder doesn't really matter what it looks like, but so y equals x plus 1. It has a y-intercept at positive 1. You may want a ruler, or you could just dot a bunch of points. So here's my first point at an intercept of y equals 1. And then I'm just going to go up 1 over 1. So it might be just as easy. You can just kind of dot a bunch of points, up 1 over 1, down 1 over 1. So this is your slant asymptote cutting through your graph. And then you can kind of already see where the elbows are going to be. You already have enough points to just make your graph. So in this region, it kind of looks like this. So it hugs this asymptote and it goes through those 2 points. And in this region, it's going to hug the 2 asymptotes and go through that point. So they're long and narrow. And once in a while, your slant asymptote will end up landing and it'll be like it'll be the short little guys like this. So you could have landed inside the little V's, but we happen to land inside the big V's. So depending on where your points end up, it'll look like this side or like this side. All right, so this is a little bit tricky. Your domain and range, your domain is still x cannot be 1, because I still have that vertical asymptote at 1. But your range now has no restriction, because these arrows keep going forever and ever because there was no horizontal asymptote. So in this problem, your range is actually all real numbers. So when you have a slant asymptote, if it looks like this, it might have a domain restriction, right? I can't be between there and there. But if it looks like this, it goes forever. All right, and then the last one I'm going to try with you, and then you can practice a couple, like what your quiz would be tomorrow, but you still have homework tonight we're going to go over, and we're going to do some of 206 tomorrow in the first half of class, going through questions, finding asymptotes, and practicing graphing some more. So it's not like this is the end before your quiz, but this is the type of question you'll have to analyze. All right, so let's do 6 together, and then you can take and try 3 or 4 problems on your own. So I find my y-intercept. So I plug in 0 for x's, and I get negative 7/5. So I need to figure out how to graph 0, negative 7/5. So that's an improper fraction. It's really negative 1 and 2/5. So on the y-axis, it's between negative 1 and negative 2. So just somewhere between negative 1 and negative 2. right? -7/5. It's more than 1, or more than -1, but less than -2, or greater than -2, I guess. All right, your x-intercept is also going to be a fraction because you're taking 6x minus 7 and setting it equal to 0. You would add 7 to the other side and divide by 6. So 7/6 is your x-intercept, which is just more than +1, right? It's 1 1/6. So on your x-axis, you're just more than 1. Skip domain and range, your asymptotes. What will make 2x plus 5 equal 0? So I would subtract 5 to the other side and then divide by 2. So -2.5. A lot of decimals on this one. X equals -2.5. So put that vertical asymptote right between -2 and -3. And then my last step is to compare the powers of the numerator and denominator. So I've got both linear functions this time, right? So we've done it when the denominator was bigger. We did it when the numerator was bigger. This time they're equal, so we just strip the coefficients, and 6 divided by 2 is just +3. So my asymptote is at y equals 3. So I can see where one of the elbows is, and I can actually assume where the other elbow will be because we didn't find any other x-intercepts, right? So if the elbow was in this region, it would have had another x-intercept over here. So I know that it's up here in the top left, but I could go ahead and plug in like maybe -3. This is -2.5. So if I try -3, I don't know, this one by hand might not be very good. Let's see. -3 times 6 minus 7 is -25. And then if I plug in -3 here, I'll have -1 in the denominator. So at -3, it's at +25. So I won't expect you to calculate a big value without a calculator, but we did kind of prove that the elbow would be in the top left. And then my domain, x cannot be -2.5 and y cannot be +3. So students completed graphs 2, 4, and 7. So here is the answer to graph number 2. So pause it if you need to pause it. And then here is the answer to graph number 4. Notice that the range was y is greater than 0 on this one. And then this is graph number 7, where we stop.